Hey class, Mr. Mao here. I feel like I gotta remind you, since we don't actually see each other in person, this is me in this tiny little bubble here. So, simple machines. This recording has failed like 3 or 4 times, and it's getting pretty late on a Sunday night. But lucky for you guys, lucky for me, I love talking about simple machines and levers. And a lot of people might think that's a little weird, but these are everywhere in the world around us. They explain so much about how the world works. They make your lives so much easier. They're literally all over the place. So this unit of simple machines, we normally we build all this cool stuff in class. We can't do that, but there's still so much that you can see in the world around you, at home, walking around the city, that you can say, oh, that's a lever, that's really a lever, and just I think it's so cool what they do to help make the world a better place. So the 6 simple machines are levers, wheel and axle, pulley, inclined plane, wedge, and screw. We're going to mostly focus on the lever and the wheel and axle, and really a lot of these simple machines are just different levers hiding in different forms. So the big idea here is mechanical advantage, and this is why we love simple machines and levers, because they allow us to change the ratio of magnitude of the resistance and effort forces. What does that mean? So the magnitude is the size of a force, and the resistance force is something you're trying to move or lift, and the effort force is the force that you're putting into that. That might be the force of a motor or the muscles in your body. So what does this mean? It means we can change those forces. It also changes the ratio of distance traveled by the effort and resistance forces. So how far these things are moving. The calculated ratios allow designers to manipulate speed, distance, force, and function. So that's a lot of science jargon, which really it allows us to make things move faster, slower, or stronger, or with less force. So by manipulating these things, engineers have come up with all sorts of tricks for changing the size, direction, and distance of forces to make these awesome machines that make our world go round. So a mechanical advantage, let's say we have a mechanical advantage of 4, or you might hear this as 4 to 1. What does that mean? Well, this ramp is a simple machine here, giving us a mechanical advantage of 4, making it 4 times easier to lift a box. So if you imagine lifting that box straight up or using the ramp, now we're going to ignore real world things like friction and heat and some other, like when things bend and move, that waste energy. But that is going to be easier to slide that up the ramp. 4 times easier, but it comes at the cost of it's got to go 4 times farther. Okay, so that magnitude of force, if we think of our push lifting that box as the effort force, noted by this red arrow here, it is 4 times smaller going up the ramp. So less effort force means we're getting stronger. That's a mechanical advantage of 4 in this case. So it takes 4 times less force, or our output force is 4 times stronger. So with 10 pounds of force, I can lift a 40-pound box. The distance traveled by the force, however, is got to be longer. So here, this is a shorter way to do it. It might be faster. So that's the price you pay. There's a trade-off, right? You can't have it both ways. You can't make a machine make you stronger and faster. That's one of the great laws of the universe, is that those come at a trade-off to each other. So we've got 4 times greater distance that we have to go to get that 4 times less effort force. So, and that all comes down to work. And we're not going to spend a bunch of time talking about this today, but work is force times distance. So it's a product, a combination of those two things. You can't change the amount of work. If we go back to this ramp, it's going to be the same amount of work. So 4 times less force, but 4 times greater distance is going to mean it's the same amount of work. If you're trying to get this box from down here to up here, it's going to be the same amount of work whether you slide it up that ramp or lift it straight up. Now, again, we're ignoring like friction and some other real world stuff, but we're going to keep it simple to start with. And we're also going to not worry about why this is a parallel distance. So it gets complicated, but let's start simple here. So the product of the effort and the distance forces traveled, this will be the same, right? Regardless of which route you take, because of mechanical advantage. So we can't change the amount of work. And you have to be careful, because in regular everyday English, the words work and force, or effort and work, might mean the same thing. They mean different things here. So work is that product, the combination of those two, and force is just the amount of like push or how heavy something is. So mechanical advantage, we've got two cases here where it's greater than 1 or where then it's less than 1. So to just kind of simplify this, greater than 1 makes us stronger and less than 1 makes us faster, right? So greater than 1 required less effort force, but greater distance. Less than 1, we have a greater input force. We have to push more on something to move that resistance force, but we have to do it less distance. And we'll talk in a second about why you might possibly want that. So mechanical advantage can never be less than 0 or equal to 0. And we'll talk about sometimes maybe why you'd want it equal to 1. So what's in the real world, can you think of a machine that has a mechanical advantage greater than 1? So this is where I'm going to encourage you as a student to actually pause and think about it. When I ask you questions, we're not in class, you can just be like, whatever, Mr. Rowell, I'm going to keep going. I want to get this video done. I might even be watching at 1.5x right now. Hopefully not faster than that, right? You want to stop and think about this stuff. Pause the video, like, what does mechanical advantage greater than 1 mean? Think about that. Think about where you might have seen machines that do that. I'm gonna wait for you to pause it and go think about that. Come up with some examples. Okay, so you're back, and we've sat here in awkward silence maybe, or maybe you actually can't thought of some things. So mechanical advantage greater than 1 means it's making us stronger. It has less effort force required. A great example I like is the can opener here. If you've ever seen an old school can opener, not like one of these ones where you turn it, but one of those where you have to like use this thing to cut open the can all around. This is a great invention, and there's a lot of neat little mechanical tricks here making it easy to open that can. Most of us are not strong enough to rip open that metal lid to get to that delicious food inside, so we have this machine with a mechanical advantage greater than 1, making that easier for us. So now, what is the mechanical advantage less than 1? And this is now where we are making ourselves weaker, right? Or we require more effort force than the thing we're trying to move. So give you a second to stop, pause, and think about why we would do that and what's an example. Okay, so hopefully you paused, hopefully you're back. And one example is in the gym. Weights are expensive. They're hard to move around. They're expensive. Well, they're not that expensive, but they're expensive to ship because they're so heavy. So if somebody wants to lift a 300-pound weight, we can trick the body into thinking maybe like 50 pounds of weight is 300 pounds with mechanical advantage in these machines. So you can like take a 5-pound weight and through mechanical advantage, make it feel like you're lifting 20 pounds to give your body a greater workout without having to have actual 20-pound weights. Another good example is the catapult, right? We've got this heavy weight on the end here. This would be like our effort force that is driving and pushing that catapult, and we're throwing this rock or boulder or whatever. So this is lighter than this force driving this, and we get greater distance, right? We want to fling that thing through the air as fast as possible. So that's the trade-off there. We're getting less force because these things are lighter, but they're going faster and greater distances. Okay, so levers, there are 3 classes of them. This is your kind of like technical definition of a rigid bar, blah, blah, blah. Engineers love to have these fancy words for basically we're like moving a flat piece of something. So vocab word you might need to know here is fulcrum. This is just the pivot or the balancing point. If you think about this one like a seesaw, right? It's where that thing's turning or hinging. So first class lever, this is kind of like your seesaw like we saw in that last slide. So this is very versatile. You can have a mechanical advantage less than 1, equal to 1, or greater than 1 based on where you put that fulcrum. And basically when you have a longer effort arm here, right, the effort is where you would put your force in, that is going to give you a greater mechanical advantage and make you stronger. You've probably used tools that work like this. A second class lever now is we think of the lever like the seesaw, right? Second class lever has the fulcrum at the end, so the resistance here and the effort is here. The classic example for this is a wheelbarrow, where you would put the resistance in here, right, that's the thing you're trying to lift. Your effort goes here at the end, and the fulcrum is the wheel. Nice thing about a wheelbarrow is your fulcrum can move, so once you get that lifted up, it's easy to move stuff around. The fulcrum on levers is often not a wheel. Okay, so that's a classic example of a second class lever. Mechanical advantage greater than 1. Wheelbarrows make it easy to lift things, easy to move stuff around a construction site. So that is where we're looking at mechanical advantage greater than 1. And the last class here is a third class lever, and this is a mechanical advantage less than 1. So this is like our catapult, right? If you imagine your effort is this yellow arrow here, it would make it harder to lift that thing. Why would you ever want to do that? Well, because then that gets your resistance going faster here. Okay, so sometimes you want speed. Think about like a baseball bat. You want to get the end of that bat going as fast as possible. A baseball bat is kind of like a third class lever. Another one, common one, is a spoon, right? A spoon is kind of like, or a fork. You want to get that food into your mouth as fast as possible. You don't have to move your hand as far if you use that spoon as a third class lever. It's increasing the distance that food travels. Okay, I'm crazy about tools. I love, I'm in this basement here that I kind of tore apart using tools like this and then put back together with other tools. So I love tools. I love building stuff. Some examples of, like I said, levers are everywhere. Pliers here. This is a first class lever. It's kind of actually like 2 first class levers sandwiched together where you have the fulcrum in the middle here. So you have your effort here, right, on the longer one, which means it's going to make you stronger. Your resistance, whatever you're trying to bend or pull or move, would go here. That's your resistance force. Your effort force is here. These are going to make you stronger. One of my favorite tools that I use to tear this place apart before I put it back together is a pry bar. Now this can be used as like a second or a first class lever depending on how you use it. If you're like trying to use it as like sort of like a first class lever to pull nails out. Sometimes you're using it as a second class lever to like try and pry stuff apart. Really fun tool for demolishing stuff. So it can be a first or a second class, or maybe even a third class lever. And sometimes I've used this in a lot of interesting ways to take stuff apart. Classic, another third class lever here is the hammer. So if you imagine this, right, the fulcrum or the pivot point is down here and your effort is here. So you want to get the end of this hammer moving as fast as possible because you need a ton of quick force to drive that nail into something. So this would be a third class lever. So your assignment is you're going to go find 6 examples of levers in the world. They are all over the place. They're literally everywhere. A door is a lever, like I mentioned. A spoon is a lever. Find 6 other examples from the world around you and put those in your notes and tell me what class is it and what's the mechanical advantage, less than 1 or greater than 1, or maybe equal to 1. And then just give me a short summary, 3 sentences about what you learned or what you thought was interesting. That summary can be whatever you want. So that's your assignment, is these notes, right? So whatever notes you've got, get those organized in Notability and get those 6 examples and upload that as a PDF for this assignment. I look forward to seeing what you find in the world around you as a lever and hearing what you think about it. Thanks for listening.